The majority of the time, we solve the systems of equations using the elimination method rather than substitution. Because substitution can get kind of gnarly. Elimination's not too bad. So you want to write it, if you're going to use the elimination, in standard form. By the way, sometimes this is also called general form, depending upon what book you're using, standard or general form, which is ax plus by equals c. So all the x's and y's on one side, all the constants on the other. And then you're going to try to eliminate a variable by multiplying either one or both of the equations by a numerical value so that the coefficients are the same. So in this particular instance, I notice if I multiply the first equation by 2 and add, that the y's would drop out. I'd have a -6 and a +6, and the y's would go. That's the kind of the name of the game. Here, if I wanted the x's to go, I'd have to have both of these the same. I'd multiply, say, the first one by -5. That would give me a -10. And I would multiply the second one by 2. That would give me a +10. -10, +10 would be 0, and the x's would drop out. But you look to the one that's going to be most convenient and cause the least amount of pain. In this case, it would be to kill y. Now, what your book does is this. They label these two, and this is to set you up, by the way, for Chapter 7. And they call the first equation R1, and they call the second equation R2. Now that's going to come down in Chapter 7. They're going to call it row 1 and row 2. And that's what the R is going to be. You can do it that way if you like, or you can, and I've always labeled mine, equation 1 and equation 2. Either way, whatever works for you. When we move to Chapter 7, this will be the notation we're going to be working with primarily, because we'll be working with matrices. So, and therefore we're going to be working with rows and columns. So that'll be the notation that's going to come out. So I tell myself, to save myself from myself, how am I going to work this problem? I said I'm going to kill y, and I'm going to multiply this first equation by +2. That gives me a -6y and a +6y, and the y's drop out. So that would be taking a 2, and I'm going to multiply that times the first equation and add it to the second equation. So that tells me this is what I'm going to do. I'm not going to do it in my head. I'm going to put it down on paper so that I know exactly what process I'm using. It says, now take 2 times this guy, all the way across. So 2 times 2 is 4x minus 2 times 3 is 6y equals 2 times 7 is 14. Then I'm going to add it to the second equation. 5x plus 6y equals 4. Notice that indeed the y's do drop out. 9x equals 18, or x equals 2. So now I have the shared x value, and the shared x value is x equal 2. I can use either of the two equations, and I go back to the original to find y. And I'll go just use the first one. So that 2 times x minus 3y equals 7. 2 times x is 2, minus 3y equals 7. 4 minus 3y equals 7. Isn't that cute? Minus 3y equals 3, or y equals -1. That's the elimination method. And 90% of the time, or 95% of the time, when doing systems of linear equations, two equations and two unknowns, you use elimination rather than substitution. Only if it looks like substitution is going to be the easier way to go.